Hi, today we will be going over OpenRocket, a free program we can use to help design and simulate rockets. First, we have to download OpenRocket onto our computer. If you have a Windows-based computer, you will need to download the exe extension installer. If you have a Mac, you will need to download the DMG extension installer. Both of these are available in the description of this video. Since I have a Windows computer, I will be downloading the Windows version, although the steps are virtually identical on a Mac. To avoid issues with your computer not having the proper Java software, the included link has Java prepackaged with OpenRocket, so it should work without any additional installations. The files are hosted on Dropbox, but you don't need an account to download OpenRocket. Just click on No Thanks, Continue to View. Once you have downloaded the program, go ahead and open it up. A white screen with a few icons should pop up. From this screen, we can build and simulate our rockets, and even use software to fine-tune our parts for optimal flights. To start, let's model a common Level 1 rocket, Lock Precision's High Tech. It's a good idea to have a pair of calipers and a tape measure handy, so you can measure all of your components. It's important to get good measurements so our simulations can be as accurate as possible. We can start by adding a nose cone by just clicking on the nose cone icon. From here, we can enter in all of our parameters for our nose cone, and even change the material it's made of. There are many different kinds of nose cones out there. Our nose cone happens to give an ogive shaped nose cone and a shape parameter of 1. It has a nose cone length of 22.9 centimeters, and a base diameter of 6.6 centimeters. We can go ahead and check the automatic box to automatically set the rest of the rocket body diameter to 6.6 centimeters. We have a wall thickness of 0.318 centimeters. We can again go to component material and select our material, which is polystyrene. We assume we will give it a regular paint job, and we can select the finish. Now we can check out the tab on the top of the nose cone configurator and look for the shoulder tab. Click on that and we will be brought to the nose cone shoulder editor. Now we can add a shoulder with a diameter of 6.3 centimeters, a length of 6.65 centimeters, and a thickness of 0.15 centimeters. In the next tab, Override, we can specify our own mass and center of gravity for this part should we choose. For now, we can leave these unchecked. In the next tab, Appearance, we can change the color of our component in the editor. This has no effect on the simulation other than changing the colors, but can be useful when things get cluttered. We can also add a texture to our rocket to aid in the photo booth, which we will go over later. The last tab, Comment, allows us to write any notes about our particular component. This can be useful when multiple people are editing one OpenRocket file, such as with competition rockets. For now, we can leave this blank and hit Close. Next, we want to add our body tube. Go ahead and click on the body tube icon, and we are met with the body tube editor. Our particular example has a length of 25.4 centimeters, and an outer diameter of 6.6 centimeters. We also have an inner diameter of 6.2 centimeters, and a wall thickness of 0.2 centimeters. We can select the material cardboard and give it a regular paint finish. You'll notice there's a button over in the top right called Select Preset. If we click on that, we can go to From Database, and we are presented with a list of some commercially available body tubes. You can do this for any component, but it's best to use your own measurements. From here, we can scroll down until we find the Lock Precision and find the body tube that matches our tube the best. If we click on the box to the left, it will be added into the preset menu. We can click on OK to go back to the editor. Now when we click on Select Preset, we can choose Lock BT256, and it will automatically fill in the values. In our case, the length is wrong. We can click on Close the editor, and we can go to Edit on the top of the toolbar. From there we can select Undo, which will also tell us the shortcut for future use. Next up, we can add the coupler. To do this, go ahead and click on Body Tube in the left window to select our body tube. We can then click on a coupler to add one in. Our coupler happens to have a 6.2 centimeter outer diameter and a 5.8 centimeter inner diameter. It has a wall thickness of 0.2 centimeters and a length of 15.2 centimeters. Now we can adjust the offset in the coupler to line it up in the middle. We can choose the relative position we like and then adjust the slider to an appropriate length. In my case, I have chosen to attach to the bottom of the parent component and move it 6.5 centimeters. Make sure to set your component material to cardboard. Now we can add in another body tube, this time 76.2 centimeters long, 6.6 centimeters outer diameter, 6.2 centimeter inner diameter, and 0.2 centimeters wall thickness. Again, make sure to set our material to cardboard. We can close the editor and select the body tube in the left window so we can add in our centering rings. We have an outer diameter of 6.2 centimeters this time, which is the inner diameter of the body tube, and a centering ring inner diameter of 4.2 centimeters, and a thickness of 0.2 centimeters, and an offset from the bottom of negative 17.7 centimeters. Now we can change the material to balsa and we are good to go. We can use the Edit menu to copy this component and paste an identical one in the same place since we have two centering rings on our rocket. Be sure to edit the second ring and move it negative 0.3 centimeters from the bottom. Now we can add in our inner tube. We have an outer diameter of 4.2 centimeters, an inner diameter of 3.8 centimeters, a wall thickness of 0.2 centimeters, and a length of 19 centimeters. We can select cardboard for our material. Click on the Motor tab will allow us to set this as our motor mount. This tells OpenRocket where to attach our motor. The next tab allows us to set a cluster and a radial position should we have one. Now we can move on to our fins. We will mostly use trapezoidal fins, and for this example, they will work best for us. You can also choose from elliptical shaped fins, or draw your own with freeform fins. From here, we can set our number of fins to 3. Our fin rotation simply revolves the fins around the body. We can leave this at 0. Fin cant will angle our fins against the wind. This can be useful for when we ought to spin stabilize our rocket. We will leave this at 0 for now. Root chord is the length of the fin attached to the body, and in our case is 10 centimeters. Tip chord is the length of the top of the fin, and for us is 7.2 centimeters. Height is the height of the fin and is 10 centimeters. Sweep length is the distance between the top of the root chord and the tip of the fin in the horizontal direction only. This can be measured either by a good ruler or a little bit of trigonometry. Our sweep length is 1.8 centimeters. Sweep angle is the angle in which the sweep length forms. You'll notice changing one will change the other. This is because they are essentially the same setting due to trigonometry. We will move our fins negative 1.27 centimeters from the bottom. From there, our fins will have a square cross-section and a thickness of 0.3 centimeters. Our fins are made from plywood. We can then set our fillets should they be large enough to affect the aerodynamics. For our level 1, chances are our fillets will be minimal, so we can leave these blank. If you do choose to add fillets, be sure to change the material to epoxy. On the next tab, we can find the fin tabs. If your fin is attached through the body of the rocket, you have fin tabs. Our fin tabs happen to be roughly 9 centimeters long by 1 centimeter. Now we can add in our launch slug, which has a length of 15.2 centimeters, an outer diameter of 0.457 centimeters, an inner diameter of 0.431 centimeters, and a thickness of 0.013 centimeters. We can move these to negative 20.3 centimeters from the bottom. Depending on your kit, these may be cardboard or plastic, but we can just select cardboard as the difference in the small part will be minimal. Congratulations, you now have something that resembles a rocket. Now it's time to add in our recovery section. We will want to go to the tube coupler and add in our shock cord. We should have around 365 centimeters of cord, and we can use Kevlar as our material. We can move it to be 15.2 centimeters from the top and 50.8 centimeters long by 2.1 centimeters thick. Now we can attach our parachute. We will have a diameter of 71.1 centimeters. The coefficient of drag, which is essentially how effective a parachute is at slowing down our rocket, of 0.80. You will have to look this up for each parachute. Most suppliers list the coefficient for their parachutes, or you can find a table online for the coefficients of common parachute shapes. We have a ripstop nylon parachute. We can set our shroud lines to 8 and our line length to 94 centimeters. We happen to have braided nylon at 1/8 of an inch thick. We can position this as best as we can. For my example, I have it at 16 centimeters from the bottom and 2.5 centimeters in length by 2.5 centimeters in diameter. The pack length and diameter won't affect the simulation, but can help you visually see how much space is being taken up. We want to be sure to set our deployment to the first ejection charge of this stage, plus 0 seconds. Now we can move on to the motors and configuration toolbar. From here, we can see the inner tube is selected as our motor mount, and we can add a new configuration. We can then choose that configuration and select a motor. We can use this to search function to easily find our motor. We can select which manufacturer makes our motor, what impulse chains we want, and even limit our motor size to the ones that will fit. We can select all manufacturers for now and search for an H110. Clicking this will highlight it, letting us know it is selected. We can click to see the details, which gives us extra information about our motor. We can also see the ejection charge delay setting near the top. We need to be careful as there are multiple H110 motors with different delay charges built in. If we look carefully at the name for this motor, we can see that it has a 14A at the end of it, which indicates it normally has a 14-second delay charge. We can select our delay and hit OK. If we had 2 stages, we would be able to select more than one motor, and we can also use the Select Ignition button to control when the upper stage ignites. Now we can move on to the Flight Simulations tab. From here, you should see one simulation per motor configuration. Right now, we only set one, so there's only one present. We can go back to the Motors tab and add a new configuration to select a comparison between 2 different motor combinations. Let's add a new configuration and add a H225 from Cicerone for comparison. Going back to the Flight Simulations tab, we can see that there's now 2 entries in our window. First thing we should do is set our launch conditions. We can do this by heading to Edit and the Preferences. We can go to Launch, set our launch site latitude to 28 north by -82.1 east, which is very close to Tripoli, Tampa. Our altitude can be 0. Our launch rod is 6 feet tall, and we will always launch directly upwind or downwind. We can always use an angle of 5, as that is our fairly standard. We can leave the wind settings as they are. We can also change our units to our preferred system in the Units tab, and add a new material in the Materials tab, and we can ignore the other tabs. Now it is time to go to the Flight Simulations and hit Run Simulations. We should find our apogee around 800 meters for both motors, with the H110 going a little bit higher. You can choose to plot this data should you like with a Plot Export button. Now for the more advanced tools. If we go to Tools, Component Analysis, we can find detailed information about our rocket. We can also go to the Rocket Optimization and use it to calculate the best shapes and designs for our rockets. For example, we can modify the root chord on our rocket, and we get a boost of roughly 13 meters based on the design it recommends. We can choose a few parameters here to define how aggressive this optimization is. We can also use the Photo Studio to generate a render of our rocket mid-flight. You can use the File and Save features to save your design, and Open command to retrieve them at a later time. There's also a Help button which gives you a guided tour should you desire a refresher. Thanks for watching.